Now, let's talk about lecture 2, which is regarding to the acquisition, recording methods, and the preprocessing. So in this recording method, the one of at that stage, I remember vividly, so-called like revolutionary development in the seismic acquisition is called a multi-channel, right? So it's not a single channel. We know that single channel is not a single receiver, and not a single geophone or single hydrophone, but even though it's not a single channel, there is multiple channels to, based on the wave behavior on the multiple channels, you can generate the seismic image of subsurface. So it's so-called concept called CMP. I think some students learned from other courses, okay? So one of the key concepts is a CMP. Right. So today we're talking about 3 parts in the recording methods. First of all, the recording the systems, and then the multi-channel recording. The third part of this lecture is pre-processing. Just basically check the quality of your data. Recording system, as we introduced in the previous acquisition, you can see they're all linked to the recording. All the sensors are connected and then linked to the recording track. And each of receiver point, basically a group of sensors, right, or geophones. That's called a single trace or single channel, right? So multiple channel means multiple traces. That's the typically for saving the energy. You know, you have a single shot, but you receive so many channels. That's basically saving, bigger saving, right? That's the one for economical consideration. Of course, in the later, we'll see multi-channel also have advantage in data processing, in imaging, right? So that's the 2 folds of the motivations. Recording system include the disk, nowadays we call disk, how to store your data, how to store your signals, right? In a permanent storage media, right? Usually, when I started a job, they use a tape. And nowadays, just use hard disk. Before that, before my generation, they use just like a camera. They record the films, right? Just print the films. Okay. So not only the seismic data, but also have acquisition geometry, acquisition sequence included. So the channels by channels, they actually list in the order of field sequence. Okay. Now, that's a typical land acquisition. Actually, that seems quite straightforward, simpler, but that actually is a pattern. You can see this pattern here. GPS nowadays everywhere, right? We use mobile phone everywhere, but that was very early stage. It's just what I said in the last session. I said seismic acquisition or seismic industry actually is a very high-tech field. Before ordinary people use GPS, seismic field, they use first. What they do, for example, you have a number of geophones, not only 2, okay, group. So this geophone is linked to one DU, data unit, right? They send this data to data unit, okay? And this one, you can link the line to something called a multiplex, where I will explain that. Multiplex, basically, you put all this in sequence. Because of distance difference, so arriving time actually different. They have a time delay. So multiplex, you need to somehow correct the time delay, okay? And You transpose this to your workstation, and that workstation transfer the digitized data to your data store. You can see this pattern is quite advanced, right? Digitized data recording. That's of course obviously that when they apply a pattern, everybody have used the digitizer, right? And then now at that time they also say, okay, you do not use this one, you use called GPS. But the GPS in this pattern mainly for the position, so where is the receiver. But nowadays, the new pattern, if you apply, will be the data sent to your GPS and they come back, right? So that's the recording system. This gives you the overview of generation by generation of a recording system, right? Before I started my first job, they use like geophone like this. You have a geophone, and the data is not digitized in the far end. It's digitized as in the workstation, right? So this analog data transmitted through the cable. Typical channel number is 96. It's a very typical one. So all this together 96. So this 3 into 1 unit, data unit, another 3, another unit, another 3, totally 96 channels, right? And then here is AD stands for analog to the digitization. Okay? So that's before 1970. And then next generation is called, they actually digitize in the field, right? This AD from here move to here. But it's not for each individual geophone. They have that's the stream, this stream together, this stream and that stream together, right? And then you send the digitized data to your central unit, right? So that's because you digitize in the far end. So that means you're capable to record so many data. So that means you can have 1,200 channels. You can see 10 times powerful capacity, yeah? More channels means you can, single shot, you can acquire much longer data in terms of distance, right? So economically, very powerful, right? Now, nowadays, when we started use a smarter mobile phone, actually they use similar to our mobile phone, called digitize the sensor in the field. So they do the record digitized signal from an individual sensor instead of group sensor, it's the individual sensor. So and then come back. So now we can have 10,000 channels for one shot. You can see it was like a 10, even 10. If we say 10,000, if 10 meter per receiver interval, so how long? Can easily work out, right? So very powerful now. Okay, that's the start from this century. And honestly, from this century to nowadays, there's no much big difference in terms of receiver. That's almost limits now. Okay, basically just 1,000, another 1,000 is not a big deal. Okay, so the different generation differs in A to D, analog to digitization, to digitize signal, okay? So from a workstation, move forward to the far end. So this is the revolutionary, okay? That's the acquisition recording system. Right, so digital systems. I just repeat what I said. Okay, so the digital system is connect several groups of receivers via a single pair of wire, right? Transmit to the workstation. So digitization or it's called sampling, occurs at the groups. As I said, it's for single receiver. It's not single sensor. It's group sensor. Okay, that's the point. But from the sensor, each individual sensor to the receiver point, that still use a cable, because what you record in the field, actually the physics sensor, what we record is a voltage, right? Voltage is continuous function. It's not digital function, right? You do need to digitize that. So that's the one. Now, for digitization, there's one fundamental theory, one fundamental quotation we need to remember. It's called a Nyquist quotation. So what you can record, the maximum frequency is this formula, 1/2 delta t. Okay? So your maximum frequency you want from your data is limited by 1/2 delta t. That's the fundamental theorem, fundamental principle. It's invented by this gentleman, Henry Nyquist. And this what, because, so now we just simply turn this formula, just move delta t, let's say both sides multiplied by delta t, both sides divided by f max, you end up this formula here. Okay? So this gives you the guidance for your digitization in the field. So now, before you do the acquisition, you expect your seismic signal will have the maximum frequency of this. And then when you do digitization, you should select or set the time interval, follow this condition. That's principle, okay? For example, when we're talking about ghost, one of our ghost, we're talking about the notch frequency is on 125 Hertz, remember? So that means the maximum frequency we can record is 125 Hertz. 125 Hertz, 2 times 125 is 250, right? So 1/250 is 0.004. You can see that? So you're in the field, your delta t, the maximum delta t should be 4 milliseconds. 0.004 seconds, which means 4 milliseconds, right? But if you say, I want to save my disk space, I use a delta t equal to 8 milliseconds. No, you cannot, because you need to keep your maximum frequency here, okay? But if you do that way, what happened? We will talk about later, right? You cannot do that because there's something called aliasing. You misposition of some frequency to the wrong places, okay? So that is the next frequency. So this formula, you should, in this course, there's not many formulas you need to remember, mathematical. I think probably this is the only one, I guess, you must remember. I do not give a derivation here. You must remember that, okay? Or other mathematical formulas I just said, if you understand the physics, you can write down your own equation, right? You can write out your own equation. But this one is came from the gentleman. You just need to remember that. That's easy. Okay. If your sampling called undersampled, sampling rate delta t too big, what happened? It caused something called aliasing issue, right? So aliasing issue means you have the frequency in your final frequency spectrum in the wrong places, okay? And the signal itself cannot make a correction because it already put in the wrong place. It cannot put back to the right place. If you aliased, you cannot recover. That's very important. That's why you do need to get the data, have a fine sample rate before you can do anything. Okay, what aliasing looks like, let me show you this way. You can see here. This is, let me start from again. Okay, this is a sine wave. Okay, horizontally. I cannot say horizontal here. I put up 100 millisecond. So that means 1/10 second, right? So you can work out how many hertz. What a hertz means how many cycles per second, right? So now, if I sampled as dt equal to 15 millisecond, every 15 millisecond dots here, the red dots. How can I see that one? Okay, just another one, that is 37. The LSC means if we sampled interval too large, if we link this curve, you cannot recover the original frequency. You can see that? Right? Let me see one more time, okay? I don't know how to do this, how to stop this. Let me try one more time. Come on. Yeah? Okay, now, just sample every 11 minutes. Okay, let's do the 2 steps. First of all, for this signal, the cosine function here, what's the frequency of the signal? Can you work out? What's the frequency? We need a maximum frequency, right? Delta t should be less than the 1/2 frequency. So what's the frequency here? That's 0.1 second. How many cycles here? 1, 2, 3, right? That's 3. So what's the frequency? Come on. 10 times longer. It's 1 second, right? So per second, you have 30 cycles per second. So this harmonic function is a 30 hertz. Okay? 30 hertz. So what's the next? The delta t must be smaller than what? 1/60. So what's the delta t ideally? 1/60 is 13.3, right? I'm right? No, it's 16. Yeah? It's 16.6 or 6.7. Okay. So you can see now if delta t equal to or smaller than 16 hertz, 16 millisecond, your signal can be fully recovered. If delta t greater than 16 hertz, 16 millisecond, you cannot recover the original frequency. That's the Allison issue. Mathematical, okay? I just repeat. The solid curve here, the black curve, not the red dashed curve in red, okay? The black curve is a 30 hertz harmonic function, right? If in your data, I try to keep this signal, keep 30 hertz in your data, your delta t should be 1/2 frequency, so 1/60, which is 16.667 millisecond, right? So if delta t is smaller than that, that's no problem. For example, here, delta t equal to 11, which is smaller than 16 hertz, 60 millisecond, you can see that the black curve can be fully recovered, which is a dashed red curve, completely recovered, right? Now, if I keep going, okay, it's covered. I cannot see it. Okay, this one, delta t equal to 21 milliseconds. What was the required delta t? Is 16.6, but now it's higher than that, greater than that, 16.6. So that means your 30 Hertz original signal cannot be recovered. Okay, but as I said, it's not only recovered, but it's in the wrong position. What's the wrong position? It was 30 Hertz, but now where you put? It's put in the dash curve here. Dash curve is lower frequency. You can see that? So when you sample in the red dot with a 21 millisecond sample interval, if you try to recover the curve, you end up at lower frequency. So it means your 30 Hertz frequency energy actually projected to the wrong position, which means the wrong frequency, which is much lower than that, okay? And this is the important thing, for the so-called next quotation, okay? You must follow that. You can play that. I put it in the system. If we download that, you can play this by yourself, okay? That's the important delta t here. Now, let me show you another example here. This one. You see the minutes and the second, and the minute and the hour arrows. They are in a sort of funny way to go, right? One's anticlockwise. No, one's they show the all in the but one is anti-clockwise, right? Why is that? Because the sampling rate. When you see your watch, you see the very dense time interval. You see every second, every millisecond. But when you digitize that with a large time interval, you end up this way. See that? When I was your age, I watched the 007. You can see they have a very cool, push car when they drive very fast to a castle, right? You can see when the car move up from very beginning, start very, very fast. You can see the wheel actually not move forward. When you watch the movie, actually the wheel move backwards. Do you have notice that? Because the car move very fast, but your movie actually, the digitizer, where actually like a picture by picture, right? The interval of pictures or human eyes is digitized. When you watch something, you digitize something, right? So your time interval is too large. So you see the 007, that push car, they have wheel backwards. Right? When I was, but before university, I said, oh, well, that's what sort of car, when they move forward, car move forward, but the wheel going back. I was puzzling. I said, I need this one study. Well, in my life, I need to investigate why we do it. And then when I went to university, I discovered actually it's anything. It's not real physics. That's it. So the next frequency is called 1 over delta t. So if you have a data, okay, that was talking about acquisition, talking about digitization. But now if you have a data, somebody digitized data pass on to you, your capacity is limited by this formula. You need to know exactly what's the delta t. When you know the delta t, you see, okay, in my analysis, the maximum frequency I can do is this. You cannot do anything beyond that. All right, that's the same equation, but used a different way. Right? Either you talking about frequency, maximum frequency, or you're talking about a maximum sample interval. Right? Okay. In the diagram I showed before, when you have a harmonic function, cosine function, and you digitize that, and then you just you have dots for each here, and I try to link the dots. Okay, you digitize like this, and then you try to link the dots. This whole processing, actually, we are talking about now, right? So what we do, when we do the digitization means you just assume the physics, the real physics, real world is a continuous function, but you digitize that, right? So at each position, you just have, or each time, you have just simply have a, we call it data function, data impulse, okay? And this is the digitization forward step. And then you try to recover the continuous signal. That's called the reconstruction. Reconstruction based on something called a sinc function. Sinc function. I think we have no time here to derive that. This is actually quite easy to derive, which is based on this is basically a small window. That's a window. Okay, this is another window. So Fourier transform of a window function is this, right? This is called a sinc function. What is sinc function? Sinc function means a sine function divided by the argument of sine. Okay? If the argument is 0, 0 to 0 equal to, do you know that? The numerator and denominator both are approaching to 0. What's this? That's 1. Yeah? Okay, perfect. So this is 1. And then if this is non-zero, of course, you have could be 0 or non-zero. So you have just like a cosine function, but it's a sinc function, sine function here. Okay, this is the sinc function, right? At 0 point, sine 0 to 0 is 1, and then gradually, that's sine function, but weighted by the argument of sine, you can see gradually decayed, right? That's the exact sine function here from the sine function and gradually decayed. And but at time 0 is not sine function, of course, but after the first 0 cross, that's sine function. A sine function divided by the sine phase, you can see gradually decayed. Okay, now? And for each of this point, 0 crossing based on the sine function. What is? Which means delta t here, you can see. Right? If t divided by delta t is an integer, you have a 0, 1, 2, 0 pi, 1 pi, 2 pi, 3 pi, right? So that means you can see 0 pi is 1, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. That really means the number of samples, the sample index. You can see that? Okay, so the sinc function means you can use the neighboring, in this case, neighboring totally 13, 6 plus 6 plus the central one, 16 samples to recover the signal. That's called a sinc function. Okay. Now, that was the sinc function. In the frequency domain, that's the time domain, right? You have that. So in the frequency domain, as I said, it's just like a window. Each of this like a window. So what do? You do the window-wise that in the frequency domain, we assume the signal are periodic. So what do? You only keep the first part, central part. So this I call the boxcar function. So frequency domain for frequency signal is periodic. As I said, because Fourier transform argument is sine or cosine, so that's periodic about pi, right? So you have a periodic, but you only need the first period spectrum. So you just do the boxcar, which means you multiply this to this. So you simply keep the central bit and delete the rest. That's in the frequent domain multiplication. And we learned last week, in one domain multiplication, either time or frequency. In another domain, either frequency or time will be a convolution, right? That's why we learn that transform, learn DFT, because we can easily transfer convolution in one domain to a multiplication in another domain, right? So this is the same thing. Here, time domain convolution, frequent domain multiplication. So it means if frequency multiplication become time domain convolution. So basically, how to reconstruct the signal, you use the digital signal, convolve with the sinc function, you end up the signal. Okay. In the time domain, you simply just do the boxcar window. Okay, the boxcar just like a train, a series carriage in the train, right? One of the box, that's called a boxcar. Okay. So now this diagram here gives you just two-way street, right? One is from the field data you digitize, you end up not only single frequency, but they have a periodic. After Fourier transform, have a periodic, right, which is this one. But now if you do the reconstruction, you just use a boxcar, use the central part of a spectrum, and then you end up just like a time domain convolution, get a reconstruct. So same principle applied to the either sampling or reconstruction. If we do some data processing, if we want to reconstruct some signal, you do need to use sinc function. Show you example here. If data, this curve, the continuous curve is real data, and the dots here are digitized samples. In this case, we just maybe undersampled, all right, which means data T too big. If data is too big, what you got in your data, you got only this. You do not know original signal, right? Because you have a data, which are the series of samples, which is this one, right? And what we do, we can represent this by Z transform. The amplitude here is the coefficient of Z transform terms, and the power of Z is the time index, right? The Z transform. And the Z is a time delay operator. So we replace that by time delay operator, we end up a Fourier transform, right? That's end up spectrum. So if we from this, we can generate a time frequency spectrum. And now, frequency spectrum, if we do that as we did it before, just so we use a boxcar function, that means in time domain convolution, we end up reconstruct data look like this. Now you can see this data almost completely different from the original data, right? So undersampled data cause anything, and this data looks like wrong. Okay, the one with the phenomena you can see straightforward. This one, this signal seems like a frequency lower than this one, right? Why? Because this one undersampled. Undersampled means assume that F maximum is smaller. So high frequency projected to wrong frequency, which means to a lower frequency. So you end up effectively everywhere seems frequency much lower than the actual frequency, right? Frequency means how many, within a certain distance, how many circles, right? In this one, you have so many circles, but in this one, you have much less circles. You can see apparently the frequency of this one much smaller than this one, right? That's the Edison issue. All right, that was the real data. Now I'll show you just some synthetic examples. For this one, you have like a lower frequency cosine function, which is here, 12.5 Hertz, right? Also have a high frequency that's called modulate, right? Which is 75 Hertz, okay? If totally 250, so if you have a 2 millisecond interval, you can see 1 divided by 2 times 2, which is 1 divided by 4, right? Remember? F next frequency equal to 1 over 2 delta t. Here delta t is 0.002. So 1 divided by 0.004 is 250 Hertz. Okay? So for sample rate 2 milliseconds, you maximally can have 250 Hertz. That's perfectly fine. However, if you have a 4 millisecond, the maximum is 125 Hertz. But in this case, still okay. Why? Because the interval, the sampling rate is still good enough, right? Maximum frequency 125. At the moment, the maximum frequency only 75 Hertz, perfectly fine. Okay. But now, if you double that, if 8 milliseconds, the highest frequency you can recover is next frequency, which is 1 over 2 times 0.008. So 1 over 0.016, right? So that is the next frequency 62.7. But in the data, we know that we have 75 Hertz. Your sample interval now is only have maximum frequency 6.2, so you cannot have 75 Hertz in your data. So where 75 goes? Okay, use 75 Hertz as the central point. This one, the distance from the 75. 6.2 as a reflection point. The distance between 75 and 6.2, which is 12.5, right? So basically, this one projected 12.5 Hertz lower than next. That's called a complex conjugate. Okay? In the frequency domain, you already learned this maybe in your Fourier transform. That's called complex conjugate. Okay, what's conjugate means? Here, I repeat, for this data set, 8 millisecond time interval. So the maximum frequency, so-called the next frequency, is 62.5, 62.5 Hertz, right? So 62.5 here is the maximum frequency you can have. But in your data, you actually had data 75 Hertz. So where the 75 goes? You find out the difference between 75 and the next, which is 12.5. 75 minus 62.5, which is 12.5. And this one you fold back with use 62.5 as a fold point, as a central point, just folding back. So basically, use 62.5 minus 12.5, which is 50. So this actually original 75 Hertz, no, actually in the wrong position. Where is it? It's at 50 Hertz. Okay, here at 50 Hertz. Okay. This amplitude, in fact, that's also have the phase changes, right? So that's called a complex conjugate. That's the Edison issue. In one sentence, Edison means you undersample your data, and the high frequency will be projected to the wrong position, right? And how to find out, basically based on the the distance between the true frequency and the highest frequency. You fold it back. Right, let's talk about, that was the sampling. Now let's talk about the seismic recorders, okay? As I said from the very beginning, there's at the far end of a receiver or your sensor, you do have an analog filter over there. And then you need to somehow sample that, okay? But before sample that, yeah, you also have something. You need a filter in the field. It's called a Natchez filter, because industry electricity frequencies, some countries 50 hertz, some countries they use 60 hertz, right? You need a notch filter, basically targeted at this frequency, just try to remove that in the field, okay? So this is called a Natchez filter to remove 50 hertz or 60 hertz. In your data recorder system, your data represented eventually digitized, right? In the digital way, right? And because in the digitized in the digital disks, you have limits for the so-called dynamic limits to record the magnitude. So this is called dynamic range. So most likely, if we have 24 bits, we'll talk about later how to calculate. That means your amplitude can have from negative this value to positive that value, okay, which is 24 bits means 1 bit means 0, 1, right? With a binary. So for each bit, you can switch to 1 or 0, 1 or 0, 1, 0, right? So that means you have so many combinations. 24 bits means 22 power 23 minus 1, right? So this is the maximum so-called dynamic range, right? If you have, okay, I want a very strong source, I have an amplitude higher than this, that means basically you cannot record, right? How we do in the field, we need something in the field which is adjust the recording amplitude. You just keep that parameters, and then when you go to data processing, you recover it, okay? So this is called a gain control, right? Gain control. In the receivers, next to the source, you usually have high amplitudes, but in the far end, the amplitude becomes, signal becomes much, much weak, right? But you want to record both very strong and very weak amplitudes. So you need a very so-called wide dynamic range, okay? So what do we do? Usually we apply gain. Gain means not only amplify, maybe amplify far end, but also somehow suppress the neo and source receivers, okay? This is the calculation I just showed you before. This is called bits. It's based on this formula. This formula means because we use a binary, so we use log 2, right? How many, the numbers, for example, the maximum value for the numerical number 1, 2, 3, if we do logarithm, but you take the bottom bit, but we say, for example, means if we have a 6.9, we just take 6, and the plus 1. Why plus 1? Because this bit include, basically use a 7, okay? But if we exact 7, you basically have 7 here plus 1 is 8. That's 1 bit large. So if I want to record the maximum value 123, this single value, or negative 123, you need at least 7 bit positive, negative, and all right, or 0, 1, 0, and 0, 1. Okay, this is binary. So in the recording system, pretty much in the older stage computer, you have so-called fixed point numbers. Basically, you know, for the first digits, it's 2 power 0, 2 power 1, 2 power 2, 2, 3, 2, 4, 2, 5, until 2, 6, 7. And another, this integer bit. And then for the floating point, you have 2, 0, 2 minus 1, 2 minus 2, 4, 3, okay, that's one. So that's called a fixed point. In this case, 0, 1, 0, 1, 0, 0, 1, 1. This actually you can work out. 0, nothing, 2.6 here, 2.4, 2.1, 2.03, and up 83. And for that's for integers. And that's very, very early stage computer. And then you have a floating point. They have here 2 minus 1, which means 0.5, right? And here 2 power of minus 3, which is 0.125. That's end up 0.625. Okay? So that's called a fixed point number. And then when I started my job in the industry, they call the floating point numbers. They use floating point. In my life, I do see this progress step by step. Okay? So what they do, they say, okay, I know exactly point here. We have a integer and decimal points, but also have an exponential component here, exponents here, right? That's a 10 power something. So now we can have the integer bit, we have 2, 0, 2 minus 1, that's 1.625. But for exponent here, we have 2 power 2 and 2 power 1, so that's 6. So basically, your result is 1.625, which is this bit, and multiplied by exponential part, which is 2.6, so end up this number you can see. So floating point numbers will have a same number of bits, will have a much bigger dynamic range for recording data. So how to work out a bit number based on this formula? Okay, I just already see the logarithm before, but it's just an inverse of the logarithm formula before, right? So compare the two systems. One's for fixed point, so range is fixed by number of bits. But for floating points, you can, first of all, there's a non-integer representation, so everything is decimal points, right? And they can have the integer part and the numbers after decimal points, but also have exponents, right? So combine them, they have a much wider range than the fixed point. Okay, that's the thing. But why I'm still talking about fixed point? Because some, typically for university practice, if we do the field work, most likely we use a very old-fashioned recorder, right? That's fixed point. Because if we student use a hammer as a source, the energy is limited, so the dynamic, also the recording line is not that long. Okay, so dynamic range is not that required. Dynamic range is not that high, not that wide, right? So actually, this was still quite useful, particularly for the engineer work. For example, if we do the investigation for construction, for building, right? Use something, but for oil or gas exploration, that's already outdated. Nobody uses it, right? But the geophysics method here is not only for oil or petroleum industry, but for everything, right? For the civil engineering work, for the construction, for building, right? Right. So again, as I said, you can modify your signal to fit into the dynamic range of your system by applying gain. Gain, in terms of units, we use relative units, which is a logarithm. Okay, so in the dispose this dB as the units, which is 20 times the amplitude logarithm. Let me show you the formula here. So this unit's power in dB is, you have I said it's relative. You can have a reference power. Okay, so that means maximum here is 1. Maximum here the 1. So log whatever the base here, log 1 is, anyone know? What's log 1? Log 1 is 0. That's right. So that means everything here most likely becomes negative. Because usually P naught is a maximum, right? So that's negative. Negative multiplied by 10, that's we call it dB, right? So sometimes say 50 dB. In fact, in the Maxwell formula here is a minus 50, all right? But we just ordinarily we say that 50 dB, okay? Right. Power is squared of amplitude. Power is squared amplitude. So that means if we use amplitude to the normalization here, you should multiply by 20 because there are 2 here in the logarithm. Here you can move the 2 to the front, right? So it depends on how we do the calculation. If we use a power, logarithm 10, here by 10, multiplied by 10, but here multiplied by 20 because this 2 here came from the power, okay? That's the same thing. So dB measures relative strength. Dynamic range, I already mentioned a few times. Dynamic range means you can record the strongest and the weakest amplitude same time. That's the dynamic range. But dynamic range is not the largest amplitude, okay? If we talk about 1,000, another one, say maximum amplitude 1,000, another one's maximum maybe 0.1. Okay, they are not really means different dynamic range. Dynamic range means the difference between the strongest and the weakest, right? Because normalized, right? So you do not worry about the biggest and smallest, but normalized, use a dB here in the dB unit, right? And the dynamic range controlled by how many bits per number. Okay, so I think the mobile, most computer nowadays use 60-bit, right? But in the field, well, the maximum at the moment, the maximum bit is 24 only. Okay, 24. So in your data processing, you may have a 60-bit computer, 64-bit computer, but in the field data, only 24. I think I said here, nearly all modern systems use a 24-bit. Okay, so 24-bit means equivalent to 144 dB. This is the formula here. Okay, actually it's 23 here. I might as well say nearly that. Right. So recording medium, I just quickly go through that. Originally use a photographic. That's why we call seismic trace by trace, right? It's actually on the photographic paper. Nowadays, even we have a sequential samples, we still call trace. That's where the trace came from, right? And then we use magnetic strips. That's a single trace. And then later stage, use the taps, just like that day when we went to the cinema, they used the taps, exact taps we used for the field seismic acquisition and data processing. But modern days, we use hard disk, right? Hard disk in the field. And the recording format, that's quite a few standard one. Different company, they use different one. And but when you transfer data between companies or between processing houses, you use a standard one, usually called SEG-Y format. SEG-Y, SEG means Society of Experiential Physics. Society of Experiential Physics, okay, they have set up the standard format. The standard format have a so-called the recorder header, just whole system, but they also have just a recorder header, but also have a binary trace header, recorded information, who required, when required, everything over there. And then for single trace, for each trace, you have a trace header. Trace header includes sample interval, right? Or including the, as I said, you in the field use a GAN, right? Or field use a notch filter, all this information recorded in the trace. Because the line is so long, some area in the mountain area, some in the desert area, maybe the field is different. They are all recorded here, and then you trace by trace in sequence, right? That's the system. Although you see the data like a matrix, but actually in the data format, there's a header and the whole file header, and then the trace header, trace header, trace header, trace. So just like a train in the linkage header. All right. So just like a matrix, you just put each individual column one by one next to each other. Okay. So this typical SEG-Y head, you have information here, field, short interval, what's the project name, where it did that. This this one in Russia, this example. That is the trace header, the data sample format, where you put. Okay.